let us first have an overview of this topic as to what it consists of. So, in refraction, we have the following topics. So, first is, we need to define refraction. Then, after defining refraction, we need to understand it. So next is the process of understanding refraction both at the experimental level. So from experimental point of view, we need to understand refraction viewpoint, and from theoretical viewpoint. So at this point I would like to also tell that, refraction was better understood experimentally first as far as history of, physics goes. It was first experimentally demonstrated, it was understood, but the theoretical understanding, the deeper understanding came only much later when theories were developed, when electromagnetic theory of Maxwell was developed. So we need to understand refraction. Then next we move on to considering a few examples, and with the help of these examples we need to see how the phenomenon of refraction is taking place in nature and also with human life, how it is associated in human life. So considering examples, the next thing is, we need to understand, we need to analyze this law of refraction. So next is, you have this law of refraction which is also called as Snell's law. Now we need to analyze this first. Now what do I mean is over here, see, analyzing this law is important because you are going to apply this law when you study the exact phenomenon relating refraction, right? So first let us be clear with this law. What does this law stand for? Okay, and then we can move on to applying this law. So this is, next is, we move on to applications of Snell's law. Herein we come to problem solving, so application of Snell's law. So, in fact, in refraction you have only this law, and you have to see how you have to apply this law to various geometries. So, you might have many geometries of the separating surface, but then in class 11th and 12th we limit our geometry to a certain type. Okay, so first we'll study refraction across single plane surface. So the boundary is a plane. There is one medium 1, and this is medium 2. And the boundary separating these two mediums is a plane surface, right? So single. Next you can have double plane surface. Example of this would be a parallel glass slab. So this is medium 1, this is medium 2, and this can be either one or it can be some other medium as well. So a ray of light when passing on from this medium, at this medium, so it would undergo refraction, and again over here when it strikes over here, again it would go refraction. So over here we are not going into the detail, but over here I am just highlighting what we need to study. So this is 1, this is 2, right? This is third is single spherical surface. So, let us say you have a beaker, so a round beaker, there is water over here, and let's say there is a fish over here, right? So, and let's say there is a man over here. So, when man observes the fish, and let's say this is spherically curved, this surface is spherically curved. So, when this man observes this fish over here, so what will he see? He will see the fish not at the position at which it is, but at a different position. But over here we are not going again into the details. We are just saying that this man, when the light comes from the fish, it is going to bend at this boundary. So the light is undergoing refraction at this boundary. So this is single spherical surface, and then you have this double. Refraction and double spherical surface. So you have, let us say, again the same beaker, but now let's say, there is an object over here, and there is an observer over here. So if an observer sees the object, so the light from this object undergoes refraction once over here, and again after traveling it undergoes the second refraction at this boundary. And both these boundaries are spherical, right? So this is an example of double refraction at double spherical surface. Another very important example is that of a lens. So if you have a biconvex lens, or you have variety of lenses, let us take this simple one case. So when you are observing an object from this part, again the refraction is taking place at this surface and this surface. So we'll be considering these sort of examples, right? So this was a very brief overview of the topic of refraction, how we are going to study it, the systematic manner in which we are going to study it. So let us begin our study then now. So the first thing that we are going to do is defining refraction. So refraction is the bending of light as it moves from one medium to another. Right? So let me draw a diagram. So 1 minute, this was, So let's say you have this medium 1 and medium 2. You can take this example, this is air, this is water, two very common examples. And let's say light is coming from this medium, striking this interface. This is plane of separation between the two medium, right? At a certain angle with the normal to the surface, right? This is theta I, that is angle of incidence. And after it passes through, it bends, right? So it is going to bend. And since, I'm already doing this diagram with, assuming that we already know the law, but this diagram I have just bended towards the normal. Right now I am not explaining this, but let us say it is bending. All we are interested is that for now we are saying that it would have gone straight if there was no change in medium, but however, because of the change in medium, it is bending. So, this angle of the ray in the second medium is is called angle of refraction. And this is equal to theta r, right? So angle of incidence and angle of refraction. So what I have shown diagrammatically over here is the phenomenon of refraction. A ray of light which is coming from one medium, striking the boundary which separates the two different mediums, and at the boundary it undergoes deviation from its path, right? And in this case it is bending towards the normal. So it might also happen that it could bend away from the normal. So we will get into the details later on, but all at this point, while we are defining refraction, we are saying that the bending of light from its original path is termed as refraction. So I hope this is clear. Now, we have defined refraction with respect to a ray of light. But remember, we are going to study refraction within the domain of ray picture of light. So, when we are studying ray optics or geometrical optics, and in that there is one topic called as refraction. So, in this ray picture of light, we always assume that whenever a light is being emitted by a source or from a secondary source, when it is reflected from its surface, that light is traveling in the form of series of rays, right? So when we are trying to understand refraction at a very basic level, then we just consider one ray. Although you never encounter a single ray in a practical example, but then to begin with, it is very good to just take a very simplistic picture, right? So we are not considering the actual detailed picture of light, that is the wave picture of light, which we'll be doing in wave optics. So there are two pictures of light, which is the ray picture and wave picture. So we are going to study refraction, keep in mind, with the help of ray picture of light. And we are going to reserve this more detailed wave picture of light to study the phenomenon of interference, diffraction, and polarization. And let me say, for the point of view of completeness, so ray picture of light, which is a very simple picture, suffices to explain completely the phenomenon of both reflection and refraction. So these are the phenomena that we encounter while the light is propagating. So in propagation of light, you encounter these different phenomena, right? So we have taken this refraction, right? So now let us move on to understanding of this phenomenon of refraction. So keep in mind, we are going to understand all this within the domain of ray picture of light and not wave picture of light. Although we can still understand refraction from wave picture. So refraction, understanding refraction. So as it was, historically, refraction, the phenomenon of refraction was first discovered by Snell. He saw that, that light got deviated when it traveled from one medium to another. So if I take a common example, if you see, let us say you dip a pencil. So I am dipping a pencil in water, but then what would you see is, you would not see this to be a straight line. You would see it to be bent. So this pencil, which I am drawing it like this, so if there was no water, it would be a straight line, but since there is water, Okay, let me just draw this. So, this portion of the pencil which is in water is going to get raised. Each portion of it is going to get raised. So then, this portion is not in line with this portion, which is not dipped in water. So basically you see the bending of pencils is happening due to refraction. A more simpler example would be, let us say you have a beaker again and then there is water. So if you have a coin at the bottom of the container and let us say the depth is h, but then when you see from the eyes, normally over here or even obliquely at an angle, you can see this coin is not going to appear at the bottom, the depth is going to change. It is going to appear as if a little bit shifted upwards, right? So this shift is going to depend whether you're going to see it normally or whether you're going to see it obliquely. So there is going to be shift due to refraction. So like this, you can consider so many examples. In fact, the whole of problem solving is considering different situations and analyzing all those situations quantitatively. So, examples, we are going to encounter so much in problem solving. So let us not, go too much into the examples. For now, we are just introducing the concept of refraction from, just considering the example. So these two examples will suffice for that. Now let us move on. What did Snell discover? So he discovered a law relating this phenomenon. So what was that law? It can be summarized in the following mathematical form, that is sine theta I by sine theta r is nr by ni. So for him, this was just an empirical constant. When Snell discovered it, it was an empirical constant, also given the name index of refraction. So he saw that, whenever light traveled from one particular medium to another particular medium, then the angle of incidence, angle of refraction, the ratio of these two, the ratio of the sine of angle of incidence and sine of angle of refraction was turning out to be a constant, right? So this was turning out to be nr by ni. Again, these were two constants relating to the second medium and to the first medium. So this Snell's law can also be written like this: ni sine theta I is equal to nr sine theta r. Now this is as far as experimental discovery of refraction of light is considered, the law relating it. So this was the law relating it, and also the first basic premise, which is also there in law of reflection, is that the incident ray refracted ray and the normal lie in the same plane. So this is the common thing of both law of reflection and law of refraction, but the additional new thing that turns up in refraction is ni sine theta I is equal to nr sine theta r, whereas in case of reflection you have this angle of incidence, theta I is angle of reflection. So this is as far as reflection is concerned, and this is as far as refraction is concerned. So you see, even in this law of refraction, if you were to put ni equal to nr, that means that both medium are same, then obviously there is no refraction. Yeah. So theta is equal to theta r. Then it goes undeviated. Right? So in reflection, the light is bouncing back in the first medium itself, but in refraction, in this case, it would just go undeviated. So it would just go undeviated. Right? So now let us move on to the theoretical understanding of refraction. So, theoretical understanding of refraction. Newton came up with his corpuscular model of light to explain refraction. That was the first attempt, and a flaw was found out later on that it was not working. So we are not going to go into this model of light. Then this refraction, this phenomenon of refraction can be explained using three viewpoints, three different viewpoints. So first is using Fermat's principle, you can explain. Again, this is within the ray picture of light. So you are treating light as a ray. Then you have Huygens principle, but to understand refraction, you need a wave picture of light. So this Huygens principle is based on wave picture of light. So more to do with wave fronts. Now the last of all, which is the detailed description of light, is Maxwell's electromagnetic wave theory. Right? So you can try to understand refraction from all these three different viewpoints. Right? So we don't want to do the last two now because this is reserved in the chapter of wave optics, and Maxwell's EM wave theory is too comprehensive to study at the level of class 11th and 12th. So later on, when you do a separate course in optics, as you do in BSc physics, or then even in BTech engineering physics, you do this a separate course. Therein you study optics from Maxwell's EM wave theory point of view. So for now, it would be just sufficient to understand refraction from Fermat's principle, taking this as our fundamental basis for the understanding of refraction of light. So what does Fermat's principle say is this, that let us say you have this point, and let us say this is there. So this is the source point, and this is the destination. Now let us say the light being issued from this source is reaching over here. What path will it take? Will it take now this is medium 1 and this is medium 2. So it is traveling with different speeds in these two mediums, right? So light travels with different speeds in different medium. Now, will it take the straight path? Now, you also know that, let us assume that V1 is greater than V2. So this is a rarer medium and this is the denser medium. So in rarer medium, light travels much faster than in the denser medium. So light can travel much faster in this medium and slower in this medium. So what would light, Fermat principle says that light takes the least time to reach from one point to another. So it travels the least time path, not the shortest distance path. So obviously this path which we have outlined over here is the least distance path, but light is not going to follow that. It is going to follow the least time path. So it would rather prefer traveling more in this medium because it can do so with the higher velocity than in this medium. So what I can do is I can make it, over here, there, yeah, there. So you see, in this in this path, when the light is traveling from here to here and then reaching its destination over here, it is traveling a shorter path over here. Now you would expect that, let us say, it travels at this point and then just goes right over here. So however this appears, will this take the least time? We don't know. But all we are saying is, in this medium it is traveling the shortest path over here. So basically you will have to solve this problem using calculus. So you will have to designate, you will have to get the total time expression as a function of where it is going to strike, and depending on where it is striking, the angle is also going to change, right? So what I mean to say, we are not going to do this totally over here right now, but you can convince yourself that the least time path will be somewhere in between these two extremes. It will be somewhere. So that exact thing you will have to find out using calculus. So at this level, we are not going to into the details, but if we do that, then we can do that. We can differentiate this time with respect to this. You can get the expression of time as a function of this distance, let's say x, and then you can put dt by dx to be 0, right? You want time to be minimum. So for minima, this is the general procedure of calculus, right? So you can do that, and then what you get out of that is this, is sin theta I by vi is equal to sin theta r by vi. So let me just explain this once again. So this is, what it means is, so this was the source point. So this is the angle theta I, and this is the angle theta r, and this is the destination point. So this is, it is going to travel with speed vi in this, vr in this. So when you differentiate this, when you differentiate time as a function of x, because x, this is fixed, right? So this y is fixed, only this x is varying. So as x is varying, theta is also varying. So basically what is happening is, this theta can be related to x over here. So after differentiating and putting it to 0, you get this condition. And this condition is not very different from the Snell's law. So for that, you need this understanding that C by V is equal to index of refraction. So this index of refraction, which was, an empirical constant in Snell's law, this empirical constant can be related to the ratio of speed of light in vacuum to that of the medium. Right? So this is coming from theory, and this is an empirical constant, an experimental constant. And you see, this is a relation between theory and experiment. So basically you can multiply C both the sides, and now C by Vi is Ni, so Ni sin theta I is equal to Nr sin theta R. So what I mean to say is, you get Snell's law derived from theory. So this law, which was experimentally discovered by Snell, can also be derived from Fermat's principle. Now what is the advantage in this picture is that you have understood this the bending of light from another viewpoint, from a more fundamental viewpoint, and that is that light is somehow following this strange principle of least time. It is following that path to reach the destination which will consume the least time. So, if you take that as your fundamental principle, then this law can be arrived at. So, this is one thing. The other thing is, but again, so fundamentally if we want to know why is light changing the path, then the reason would be that light, since light travels with different speeds, in different medium, because of this, it changes its path. So if if the light wouldn't have changed its speed while traveling from one medium to another, then it would always follow the same straight line path. So basically now we have got the theoretical understanding as to why the light bends when it travels from one medium to another. It is because it changes its speed, it also changes its direction. So the two are related. So this is the fundamental understanding of refraction. Now let us move on to the analyzing of Snell's law. So let us analyze this Snell's law before considering some problems. Now let us consider n2 to be greater than n1. So if n2 is greater than n1, that means light travels with a slower speed, because n2 is c by v2, right? So if n2 is greater, then v2 is lesser. So basically a denser medium means the light is traveling at a slower pace in that medium. It is traveling with a lesser speed in that medium. That is what it means by saying that the light, that this medium is denser. Okay? So, if you see, if n2 is greater than n1, then sine theta 2 should be less than sine theta 1 for this equality to hold true. So if sine theta 2 is less, that means we can also say if theta lies between 0 to 90, theta 2 should also be less than theta 1. That means when light travels from rarer to denser medium, so rarer to denser medium, when light travels from rarer to denser medium, it bends towards the normal. And the opposite is the case when it travels from, so this is light traveling from rarer to denser medium. This is case one. Another case would be light traveling from denser to rarer medium. Now let us say this is n1, n2, and now n1 is greater than n2. So what would happen is, instead of following this path, it would bend away from the normal. This is theta r, this is theta I, and theta r is greater than theta I. Right? And in this case, theta 2 is lesser than theta 1. So these are the only two cases, but then you would encounter an interesting situation later on. See, what would happen if I continue to increase theta I? So in this case, in the second case, when the light is traveling from denser to the rarer medium, what would such an extent that now the refracted ray is almost grazing the surface. Because see, as you increase the angle of incidence, the angle of refraction also increases, and a point would come wherein it would just go tangentially to the surface. So, this is the point wherein we say this angle is reached. Now, this angle is termed as critical angle. Because why it is so critical? Because if you increase this angle further, the light is no longer going to get refracted, it is going to get reflected back. So if you increase the angle greater than the critical angle, then what is going to happen is the light is going to get reflected, totally internally reflected. And it goes back into the same medium, and when it gets totally internally reflected, it follows the same law of reflection. So theta I over here, and this angle is also theta I, the same angle at which it is going to get reflected, right? So now let us move on to problem solving. The first problem reads as follows. A ray of light is incident on a transparent glass slab. Okay, so you have a transparent glass slab of refractive index √3. If the reflected and refracted rays are mutually perpendicular, that means now this is the refracted ray, and this is the reflected ray. Now these two rays are mutually perpendicular. Okay, so it is given that, then find this angle of incidence. We have to find theta I. Okay, so you have been given these two information in this problem. One is the refractive index of this medium is √3, or normally we assume the refractive index of air to be 1. And the other is that these two rays are mutually perpendicular. Now, before solving this problem, I would like to tell one thing, that whenever there is a discontinuity in medium, simultaneously both this phenomenon takes place. Simultaneously reflection as well as refraction, both are going to take place. Now only the fraction of light which is going to get reflected and refracted will vary from one medium to another. So it depends on the pair of these two mediums, how much of it is going to get partially reflected and partially transmitted. But one thing is very clear, that both the fractions will remain. It cannot happen that 100% of light can get either reflected or transmitted. You can get very close if it is a very polished surface, as is the case of mirror, and almost 99.9% of the light is going to get reflected back, but still there is going to be a minor fraction of light which is going to get transmitted. So one thing this problem is making us aware is that the phenomenon of reflection and refraction is going to take place simultaneously. Now in this case it so happens that the reflected and the refracted ray are mutually perpendicular. So you need to basically apply both the laws of reflection and refraction. So if I apply the law of reflection, then what I can draw in my figure is this, that if this is theta I, then this is going to be theta I, right? So this is the application of law of reflection. Now, for law of refraction, let us say this is theta r. So now I can say, if I want to apply 1 into sine theta I is equal to √3 into sine theta r. So this is the application of Snell's law. But then, you see, I need to relate. In this equation, I cannot get the value of theta I and theta r. So these are two different unknowns. So let us relate this. So theta I plus 90 plus theta r is 180. So and then theta r to be 90 minus theta I. Now you can substitute the value of theta r over here. So you get 1 into sine theta I is equal to root 3 into sine of 90 minus theta I. Now this is sine theta I is equal to root 3 into cos theta I. So tan theta I is equal to root 3. And you know that the solution of this, if the angle is between 0 to 90, theta I is equal to 60 degrees. So this is the angle of incidence for which the refracted and reflected ray are mutually perpendicular. So this will be 60 and this will be 30. So in this situation you see that the light is bending a great amount. The refractive index of this medium is root 3, which is 1.73, and this is 1. Now just with these two pair of medium you see that the light has bent by an amount of 30 degrees. This was 60 degrees, it was going like this when it was going like this. Right, this whole angle was 60 degrees. Now it is only 30 degrees. So the angle of deviation is 30 degrees. Right. So I hope this is clear. We have solved this problem. We can consider yet another problem, a simple problem. Let us move on to that. Another problem says light is incident from air on a liquid layer at incident angle of 30 degrees. So an incident angle of 30 degrees. After moving through three different liquids of different refractive indices, three different liquids, and the refractive indices of these liquids are going to be 1.1, 1.2 and 1.3. And after that it enters water. Refractive index of water is generally taken to be 4/3 or 1.33. So find the angle which the ray makes with the normal in the water. So it is going to bend. Obviously this is air, so it is 1. So this is going to bend towards the normal, right? Again it is going to bend towards the normal. Again it is going to bend towards the normal, and again it is going to bend. So if you see it is going to keep bending, one observation is the light is constantly moving from a medium of lower refractive index to a higher refractive index. So the light is moving from a lower refractive index to a higher refractive index. So it is going to bend towards the normal. Right? This is clear to us. This one thing is clear to us, that it is going to bend towards the normal. Now if I apply Snell's law, 1 into sine 30 is equal to 1.1 into sine theta 1. So now do I need to keep applying Snell's law in each of these medium, or it doesn't matter? So let us first anyway apply this. So 1.1 again into sine theta 1 is equal to 1.2 into sine theta 2. Again we can write 1.2 into sine theta 2 is equal to 1.3 into sine theta 3. 1.3 into sine theta 3 is equal to 4/3 into sine theta 4. And we are asked to find theta 4. So basically we don't want theta 1, theta 2, theta 3 anyway. So what we can do is we can multiply these four equations, the left hand side with the left hand side and the right hand side with the right hand side. So what do we get? When we multiply, we see this gets cancelled. Even this everything is getting cancelled out. So finally what we are getting is 1 into half, that is sine 30, is 4/3 into sine theta 4. So sine theta 4 is equal to 3/8. So theta 4 is turning out to be sine inverse of 3 by 8. So we see that the angle with which the light is going to emerge in water does not depend on the history, right? On this. It just depends on the refractive index of the incident first medium, the angle, and obviously the refractive index of the last medium, right? This is the this problem is basically given for us to realize that you might keep any number of mediums in between over here, but this will not matter